Welcome to today's Explainer. We're diving straight into the solo growth model to figure out exactly how societies find that perfect balance between building for the future and actually enjoying life today. Have you ever wondered why some economies thrive while others completely stagnate? Or how a country decides between saving for tomorrow versus spending today? Well, today we are going to unpack the mathematical engine behind those very questions. Here's our roadmap for today. We'll start with the capital tug-of-war, then look at reaching the steady state, how savings actually impact growth, the golden rule, and finally, how to maximize our consumption. Let's get right into it.
Part 1. The Capital Tug-of-War.
Picture a giant factory floor. You've got this constant tug-of-war happening in every economy around the world. On one side, there's investment. This is all the money spent on shiny new equipment, plants, and upgraded tools, pushing your capital stock up. But pulling hard in the exact opposite direction is depreciation. This is just the inescapable reality of things wearing out. Machines break down, computers get old, and tractors rust. This force drags your capital stock right back down. So to figure out if our overall machinery, our capital stock, is actually growing, we just take those new investments and subtract whatever's falling apart. It's a pretty simple equation when you think about it. The change in capital stock is literally just investment minus depreciation.
Let's peek under the hood at the mechanics here. Investment per worker, which we'll call I, is driven by the saving rate S multiplied by our output Y. And since output depends on capital, we can just say I equals S times F of K. On the flip side, we assume a specific fraction of capital wears out every single year. We call that the depreciation rate, or delta. So if your capital lasts 25 years on average, your depreciation rate is 4% a year. That means depreciation per worker is just delta times K. Bringing it all together, the net change in our capital is the investment we're adding minus the depreciation we're losing. It's a fundamental trade-off, really. A higher capital stock means way more output for sure, but you're also going to suffer a much bigger total amount of depreciation.
All right, moving to part 2, reaching the steady state. Eventually, this tug-of-war has to result in a tie. We call this specific balance point the steady state, or K-star. At this exact level, your capital and output stay totally constant over time. Why? Because the amount of new investment exactly equals the amount of depreciation. The effort of building new machines and the reality of old machines breaking down perfectly cancel each other out. Your capital stock is neither growing nor shrinking. Now, this steady state is a huge deal because it represents the ultimate long-run equilibrium of the economy. Think of it like a magnet. If an economy starts out below the steady state, investment is beating depreciation, right? So the capital stock is going to keep rising until it hits that balance point. On the flip side, if an economy starts out artificially rich in capital, meaning it's above the steady state, well, capital is wearing out way faster than it's being replaced, so the stock will inevitably fall. No matter where you start out, the economy naturally gravitates right back to this steady state. Let's look at a quick mathematical example to see how this shapes up. We start with a standard production function for the whole economy. To figure out what this means for the average person, we just divide both sides by the labor force, L. If we translate all this algebra into plain English, the final simplified equation tells us that an economy's output per worker is simply the square root of its capital per worker. Pretty neat, right?
Now, obviously, tracking an economy year after year just to see where it settles would be super tedious. Thankfully, we have a shortcut. Because we know the steady state is where capital growth hits absolute zero, we can just rearrange our formulas into this specific equation. K star divided by output equals the saving rate divided by the depreciation rate. This lets us easily calculate our long-term equilibrium right from the start without any guesswork.
Which brings us to part 3, how savings impact growth. Okay, picture an economy comfortably cruising along at its steady state. But then society suddenly decides, hey, let's save more of our income. Boom. This increase in the saving rate causes investment to immediately jump higher. But wait, the existing capital stock hasn't changed yet, so depreciation stays exactly the same for the moment. Suddenly, investment exceeds depreciation. This creates a massive surplus, driving the capital stock up year after year until the economy finally hits a brand new, higher steady state with more capital and more output. This reveals a really profound takeaway about growth. The solo model shows us that a high saving rate totally guarantees a large capital stock and high output in the long run. But does it guarantee endless, infinite growth? Actually, no. Higher saving definitely leads to faster economic growth, but only temporarily. That accelerated growth only happens during the journey to the new steady state.
Once you're there, the growth level's right off again.
Now this brings up a fascinating plot twist. You might be thinking, well, if higher saving means higher output, why not just save absolutely everything? And yeah, if a nation saves 100% of its income, it absolutely gets the largest possible capital stock and the maximum possible output. But there's a huge catch. We'd literally starve. I mean, what good is all that incredible output if none of it is ever consumed? We don't just care about hoarding factories. We care about the goods and services we actually get to eat, use, and enjoy today.
This brings us to part 4, the Golden Rule.
Think about it. A benevolent policymaker doesn't actually care about just building the biggest factories in the world. Their ultimate goal is to maximize the well-being of real people. We want to find the steady state that gives us the absolute highest level of consumption. And in economics, that specific, perfect steady state value of capital is known as the Golden Rule level of capital. To figure out how much we actually get to consume at the steady state, we just take our total steady state output, that's F of K star, and subtract the chunk we're forced to spend just to replace depreciating equipment, which is delta K star. Whatever's left over, that's our steady state consumption.
Here's the tricky part, though. Increasing our steady-state capital creates two completely opposing effects. On one hand, having more capital means more overall output is generated, which is awesome. But, on the other hand, more machines means way more depreciation. A much larger chunk of our output has to be diverted away from fun stuff like consumption just to replace wearing capital. Because of this trade-off, there is literally only one mathematical sweet spot, one exact level of capital that perfectly maximizes the gap between what we produce and what we have to constantly repair.
And finally, part 5, maximizing our consumption.
Let's figure out how we actually zero in on that sweet spot. Think about where an economy currently stands. If we're below the golden rule, the production function is steeper than the depreciation line. That just means buying one more machine boosts our output way faster than it increases our depreciation. So our overall consumption actually rises. But if we're above the golden rule, the production function is flatter. Buying a new machine actually eats into our consumption because the massive repair costs completely outweigh the extra output it produces. It's a losing game.
So right at the absolute peak of consumption, the slopes of those two lines are perfectly identical. The extra output from adding one more machine, which economists call the marginal product of capital, or MPK, is completely wiped out by the depreciation of that very machine. They literally cancel each other out.
Expressed as a simple formula, this is the magic equilibrium for human consumption. MPK minus delta equals 0. Or in other words, the marginal product of capital, net of depreciation, is exactly 0. This little equation gives policymakers the exact mathematical blueprint to find the golden rule capital stock for any economy in the world.
But wait, here is the absolute most crucial catch of this whole model. Unlike the steady state we talked about earlier, the economy does not automatically gravitate toward the golden rule. It's not a natural magnet. A society has to intentionally calibrate and choose the exact right saving rate to hit this target. If the saving rate they pick is too high, we end up with way too much capital, and our consumption is dragged down by massive repair costs. If the saving rate is too low, our capital stays too low, and we literally leave potential output and happiness on the table.
So, I want to leave you with this provocative thought to wrap up our explainer today. We now possess the mathematical blueprint for the perfect economy. We literally know the exact formula to maximize human well-being and consumption. But actually getting there requires active, intentional choices. So are we, as a society, collectively making the right choices today to enjoy that maximized wealth and well-being tomorrow? It's something to think about. Thank you so much for joining me on this journey through the Solow growth model, and I really hope this gives you a completely new lens to view the economic world around you.